diode, we have to model both of this for conduction losses. We again, like, we're gonna see like how to model the switching losses when we have the diode goes to from conduction to off mode. We're gonna see that a little bit later. So this is what we're gonna see about the diode. Now, how about inductor and capacitor, right? So an inductor is basically a coil, right? So like basically bunch of wires like wound together, right? So like we have like windings, right? So these are like cables, like these are like, sorry, these are like wires, right? Like any conductor has some resistance, right? So we don't have a pure inductor. We always have some what we call equivalent series resistance that we can model for this one, or you can show it as RL, doesn't matter what you want to show. The same thing for capacitor. It definitely has like many components, like has plates and like conductors. So this one also has equivalent series resistance, or RC, right? So when the current goes through this, we have some power losses here and here. So that's what we have to consider when it comes to power losses in our electronic circuit. Okay, so this was basically what we're gonna see about our circuits. And like now I'm just gonna write the formulas for conduction losses for all of these four elements. Okay, so again, you don't have to memorize these formulas, but just understand them. And many of these formulas depend on the RMS values that we calculated before, so it would be handy if you write those formulas in a table so that you have access to them when you want to use them. So let's start with the transistor losses. Okay, so we said that we model the transistor like a switch which has our, let's say, drain source on, right? So this is what we want to calculate. Okay, so for our I think the calculation I'm doing, like, it's general, like, but basically you can apply it to buck converter or boost converter. So for the switch, we first of all, like, let me just write down okay, so this is a general term, right? Any function has a DC component and an AC component. Okay, if you want to find the RMS value of this variable, right, the total thing, like including the DC and AC, this is similar to like, I think this is like DC, this is AC. This is like similar to like calculating the length in this triangle here. So like this is the ILRMS, right? So this is going to be IDC and this is going to be ILAC RMS. So you can calculate the RMS value of any parameter using this formula. Okay, so for ILRMS, this is the case, ILDC squared plus ILAC squared. Okay, so we calculated this for buck converter and boost converter, so it doesn't matter which converter you want to calculate this for. You just replace these terms here. And we saw that, let me actually use capital term here. We saw that the IQ RMS it's either like square, like we calculated this, like let me take a look at my notes. So IQ RMS for both of the buck and boost converter is root D times IL RMS. Okay, so you can calculate this one, right? You find ILDC. So for example, for the boost converter was IO, which is VO over R. For buck converter was IO divided by 1 minus D. We also calculated this one. It was delta IL divided by 2 root 3. So you can calculate IL RMS. Then once you calculate this one, you have the RMS value that goes through the switch. Why do we need to calculate this? You remember that we mentioned that to calculate the power that goes through any element, we can just use this RMS value, and then the power loss in the switch, conduction loss in the switch, let me just write P sub Q, conduction loss. Okay, it's gonna be, can you guys guess what it's gonna be? It's gonna be this resistance, whatever it is, R on, multiplied by IQ RMS squared. Okay, this is a general formula. It's not a specific to buck converter or boost converter. You just have to find IL RMS. You have to find the RMS value that goes through the switch. We happen to have the same formula for buck and boost here, but like you just like have to double check your formula sheet when you want to do that. And then the power loss when this switch is on, it's going to be the current that goes through the switch multiplied by RDS on. So this is basically the first. So we calculated this one as well. Okay. The second element that we have to calculate its conduction loss is the diode. Let me actually leave this one here. Let me see if you can see the whole thing. Yes. Yeah, okay. So again, I'm gonna take a look at my notes again. So for ID RMS, for the buck converter, it was root minus 1D IL AC RMS. Okay, this is also AC. I sub D AC RMS. Okay. And it was actually the same thing for the boost converter. So this is what we have. And so just